Okay, well, we are glad to be here. I'm Brenda Royce. We haven't met. Um,
And I'm Larry
mo-
Ducrit.
and we've been working on this crazy curriculum for a very long time together, and we have some updates to share with you. So, Larry,
Okay, so we're going to tell you about what's new. You know that eWeb Life is a thing of the past. M- Documents have been moved into the Google environment. So that means all of the Word docx files are converted to Google Docs and PDFs. This wasn't completely easy because not everything survived the translation to the Google environment. But I think we pretty well fixed much of the problems that may have existed. When we went back through and checked things out, we noticed that there were broken or links or things that needed to be updated in the teacher notes. So those things should be correct, although we would be happy to hear from anybody who's out there in the chemistry world who discovers something we missed. Fire us an email, me or Brenda an email, and we'll take care of it.
yeah, and
And
our emails will be on the last slide.
our emails are on the last slide. We have also updated solutions to worksheets, quizzes, and tests.
With a big shout out to Janelle Hollingsworth for the help with that.
So one of the things that's new is we've continued the work that started in 2023 on changing the emphasis on proportional reasoning rather than algorithmic factor label approach to quantitative problem solving. As I said, it started in 2023 with Unit 1. And if you click on that, that is a link. And when you get this thing, you'll be able to click on that link to go back to the 2023 webinar to get the backstory. We're not going to repeat it now.
So that
Um,
gives a lot more of the why we did this on it and some other information.
exactly. And a big part of this is the story of quantitative reasoning, which is a serious document that Brenda wrote. And we've been tweaking for the past several years. It's certainly worth your reading because it explains why the change in emphasis, and we hope it makes sense to you.
And it emphasizes helping students understand the actual quantitative language we're using um, to recognize what some of the mathematical things are actually saying. And it just a whole bunch of things that I found really helpful over time to help kids better understand what we were talking about.
So we want students to see this proportional reasoning as a coherent reasoning practice. So it's all about sense making rather than answer getting. And you could probably go to the next bullet there.
Yeah, I would love to. Somehow I have, okay, let's see if this, there it is.
There are applications obviously beyond chemistry. That is, going to the grocery store and or trying to figure out how much carpeting to buy. There's all sorts of stuff. In any event, there's a reasoning tools that employ multiple representations. So it's not just the algebraic approach. And it's based on one core idea. Two things are directly proportional if they change together by the same multiplier. That's probably worth stating again. What makes two things proportional? If they change together in the same way by the same multiplier.
I
Okay,
mean,
Brenda, I
that
think
that is an idea that those two things are actually inherently linked for chemistry, physics, whatever, in nature itself. They cannot be separated from one another. And it's interesting, students don't always have that idea clearly in their heads that, oh, these just things are that happen in the equation. Nope, this is what happens in nature. So these two diagrams are actually in the teacher notes. It's a little activity that I found really helpful to begin the year with, helping kids understand what it means for something to be proportional, to relate. The reasoning to the reality. So again, like for this, looking at mass and volume, where the volume is in this case represented by spaces on the whiteboard, and the mass represented by chips, where one chip was 1 gram with really simple densities. But had students actually solve problems, simple problems, by telling them to get out so many chips and then either figure out the volume needed or give them the volume and figure out the mass. And it became pretty obvious. Every unit of volume has a certain mass. And then we took that and started working on how we could represent it. And you'll notice we started on this particular shot that I took with the volume they were given, the use of the density ratio, but then we switched it so that the 1 milliliter was moved under the 6 milliliters to emphasize that this volume is 6 times bigger than the 1 milliliter, which means the mass has to be changed by the same multiplier. On the next one, they were given a mass, and the students figured out how to group it together and then drew squares. They drew circles sometimes. They drew triangles. They got really creative. But again, starting with, why do we need to put the grams on the bottom? Well, because the 24 grams has to be compared to 3 grams, which is 8. So we need the volume to be 8 times bigger than 1 milliliter. And this reasoning really helped students begin to process things. The whole process was figuring out what the multiplier was. Sometimes it was a whole number, a bunch of times it's not. There it is. Another way to visualize it, we thank Mitch Sweet for this idea, was to put things in something like a data table, or they could be just written side by side. 6 grams is equal to 1 milliliter. And then you just show, I know that I have 18 grams, that's 3 times bigger, so the volume must be 3 times bigger. Or I have 30 grams and the mass is 5 times bigger. So, oh, well, I'm going to have to then have 5 milliliters because it's 5 times bigger than 1. And then relate that back to the mathematical representations. I recommend starting the year by making sure that you do this intermediate step of having the kids actually put the comparison of 30 grams to 6 grams with each other, so that they can see what they're finding is how much bigger one is than the other, and therefore the volume changes by that same factor. This Q times R is simply the mass is a quantity we measure. 1 milliliter per 6 grams is a relationship in nature, and then we are able to get the second one. And this theme of finding what the multiplier is really what all the various ways of representing are. This is one that's been in there forever that is exactly doing this. This is from the beginning. We started using PVTN tables and doing the calculations with using like V over V and T over T and N over N, instead of trying to use the combined gas law or something like that. So we start with a set of data. We represent it in a, sorry, your faces keep popping in the middle of my stuff. Show it with, with a couple of graphs to visualize what direction the change is going. That helps us make some decisions about which way our calculations need to work. But in each case, sorry, the little pictures of everybody keeps popping in the phone I'm trying to look at. In each case, we write the ratio of these in such a way that it will force, in this case, the temperature to change by the same factor that the pressure changes, by the way, the volume changes. And we can see that these two are simply comparing the size again. whether we combine them or we do it separately. It's all about what is the multiplier in this situation. If it's an inverse multiplier, well, then it's reversed. So it's if you multiply one by 2, then the other must cut in half. So we make our ratios do that for us.
I think the to me the really, if you back up, the really valuable part is that it's no longer arbitrary about your multipliers. They have to make sense. So if the
Yeah,
pressure is going down, then you have to be multiplying by excuse me, multiplying the temperature by a number that's smaller than one. If
right.
you had 1.2 on the top, then you'd be making the temperature larger.
And the graph helps illustrate that. First point to second point, both of them are going down. Um, and we didn't end up with one that had an inverse relationship in it. But
But
if everybody who's been using these materials has been doing this for a long time, this is what you were doing all along, was finding multipliers. Okay, this is one that gets more difficult for students sometimes to think through. I pulled this out of a solution from a Unit 3 worksheet, where we have a 235 gram sample that makes a 22 degrees Celsius change using the specific heat capacity. And we can set it up like this, and we can rearrange it if we need to see what multipliers we are using. And this really does help students kind of figure things out. It gets a little more difficult when you start trying to calculate the energy, because you have to think a little harder about what's related to what and by what multiplier. There is another alternative, though, that actually turns out. I had students say to me, Mrs. Royce, can I please use that proportion ladder thing again? Because this makes so much more sense than the equation. And it's like, you understand it, then yes, absolutely, it's useful. So we start by writing, instead of writing the heat capacity as a ratio, we write it out where the change of 1 gram going through 1 degree Celsius produces a 4.18 joule change. These two are equivalent. You can exchange them for each other. Okay. And then we can add in the things that we want to know and what we do know. And now we look for the multipliers by comparing down the ladder, if you will. So the first one, this is an easy example. It's very obvious that 235 grams is 235 times larger. The temperature is obviously 22 times larger. So then on the other side, we simply have to multiply in sequence by both of those. Now, if we wanted to find the temperature change and we know the energy change, then we would have to know that the energy change is going to be one of the factors, but then this mass change is, the mass change is known, but we have to take the energy change and divide it by the mass change so that both sides end up with equivalent multipliers. So so you can see that the 235 and the 222 both end up on the left side and the right side. The equivalent thing has to happen even if we're looking for something else. But there were kids who could solve this so much more easily doing it this way because they got nervous around the math and the algebra, and they found this so much easier to think about. So this is another way. This one's not in the teacher notes. We created the teacher notes and forgot to go back and put this piece in the earlier stages of updating the curriculum. So that'll come out. We've got some other ideas for how to make this hopefully make a little more sense to people. Then when I got to working with reactions, and of course we've got this lovely proportional piece here where that they come in this case we have hydrogen and oxygen, so in a 2-to-1 ratio, and each grouping of 2 hydrogen and 1 oxygen produces 2 water molecules. By diagramming it this way, the students can see the proportionality and makes it easier for them to see how to make, when you get to the stoichiometry, how to make use of things. We practice in Unit 7 diagramming to show the proportions, seeing them. Instead of simply representing a balanced equation, we represent a reaction mixture and then apply the balanced equation to it through these by grouping things up. We can read it out, and it makes a lot more sense here now. For every 2 moles of hydrogen, oh, that happened twice, there will be 1 mole of oxygen. Oh, that happened twice. So that will react to form 2 moles of water. And that happened twice in this mixture. So we can see that the multiplier is 2 all the way through from the balanced equation. Though I don't make a big deal in Unit 7 about this, but when one doubles, the other also doubles. That's language we've already had in there. But then, as I say, the magic happened. We got to Unit 8, and we are used to figuring things out with the mathematics. Okay. But what about this lovely BCA table? You know, we can now also look at it as we are adjusting the balanced equation to say what actually happens in the container. Instead of 1 mole of oxygen being used up, we are using up 2. That is a multiplier of 2, which means every other part of this change line has to be multiplied. That the balanced equation has to be multiplied by 2 to get this. If it happens to be 0.25 or 1.629, whatever it is, you just multiply that down. And this is like a giant proportion ladder. We can do all the mathematics, but again, the same students who asked me about, can I use this proportion ladder with the specific heat capacity, got to this and went, please, can I just use this like a proportion ladder? It's like, yes, you know how to explain it. You understand it. It's perfectly legitimate. And they slowly began to take on some of the math that they were confused with. Here's an example from the teacher notes of what we are explaining. Another example where you just look for a known multiplier, in this case, on the left side, 1 mole of lead, but we're using up 4, so everything is multiplied by 4. That could also be said as a scaling factor of 4. Okay, so this is really kind of the flow of ideas. Unit 5, we didn't say anything about, but you know, it's like working molar masses and empirical formulas and things like this still are proportional things that you can work with using some of these various tools, from diagramming to basic algebraic methods to the proportion ladder. They all help students understand. So, Larry.
So basically, when you go to the chemistry curriculum for the core units, you're going to see something that looks like this in Google Drive, and there are folders for each of the units. And in the past, they were zipped folders, so you had to download a zip folder, and then you had to open open it all up to see what was inside. Here, you can go ahead if you advance the slide. If you open up any one of the folders, like in this case, it was Unit 2, you'll see that there are solutions, and then there are the individual documents, teacher notes, objectives, worksheets, quizzes, review tests, that sort of thing. You can download any one of those things that you would like. You don't have to download the whole unit, although you could. If you chose to download the unit, then Google will very nicely zip the unit, convert everything to Microsoft Word docx's, which may or may not be easy for you to use. And for people who may have had some issues with formatting, we've taken all of the files for a particular unit and then put them into one Google Doc and then with a table of contents, and then we've turned it into a PDF. So you can print from the PDF and know that everything will work nicely, or you can just download this and take a peek at it and without having to open up each of the individual documents.
Yeah. And then print what pages you need out of it at any given time. By the way, anyone who's running a workshop this summer for Chemistry 1, these materials, the PDFs have been compiled so that you can actually download them if you need to help a host get binders put together. We've made sure that that's available. Larry, is there any special hints for those who are going to be leading workshops this summer?
Nothing other than what you just said. I believe
Okay.
ENA has told any of the Chem workshop leaders that these combined PDFs were available for them so they could use them to print themselves or take a look at if they want to project or show any particular aspect of a unit with without having to download each of the individual files.
Yeah. So one of the things that I was thinking about with my own Chem 1 workshop this summer, and then those others who might lead, the story of quantitative reasoning is included in the PDF, I think, front matter. Um, and we would encourage you to use that as a reading with your workshop teachers somewhere in the Unit 1 or Unit 2 area, so that after they've had an experience with some of the things you're talking about, to go through and read it, look for the language, think about what this is saying, think about what they might want to reconsider in their own teaching language, and then to be watching as they move through the rest of the workshop about how these practices are being employed
Can you go back a
on the
slide, please?
quantitative. Pardon?
Go back a slide, please. So you'll see 00 is approach big ideas. That's the title slide. That's the acceptable use document. The storyline PDF that Brenda was describing, and also a document that we've had available for a number of years, which talks about the development of models as we go through the units. Um, One of the things that David Hesnes was fond of saying is that to the students, the units in physics was just one damn thing after another because they weren't quite sure why they were doing what they were doing. But the sequence of models is explicated quite clearly in that document, which I didn't put in this slide. But if you go there and find the approach big ideas, you'll find that document in there. It's the document I had to produce to convince the editor at JChemEd to publish my article on modeling instruction 10 years ago.
It's a nice
Anyway,
overview of all the models. Yeah.
yeah. Moving on.
And of course, you know how to follow AMTA probably if you're here, but there it is.
Well, and there are, and we have to should give Carolyn and Ine big credit for making sure that these avenues are clear and available to you. And there are Google groups for the various curricular disciplines.
Yeah, we have a chemistry one as well as a general
And
AMTA one.
this presentation gives us our contact information. So we're done in less than half an hour. Questions?